In this video, we're going to continue on with Chapter 8, and specifically Section 8.2, which is confidence intervals for the population proportion P. So, to determine the confidence interval for a population proportion P, we first need to think of the most general form of any confidence interval that we're going to use in this class, and we found that in the last video. It's the point estimate plus or minus the margin of error. Okay, and so what we need to do now for this particular problem is to find the point estimate or point estimator and the margin of error based on that we're looking for P. So what is P again? P is the population parameter. Okay? So we always have a population parameter that we're interested in. In this case, it's P, which is the population proportion. Okay. The point estimator that we're going to use to estimate P, which is the population proportion, is P hat, the sample proportion. Okay, so hopefully that's pretty self-explanatory. We're going to use the sample version to help us try to find some information about the population version. So we're going to use P hat. So that's our point estimator. When we actually find the P hat in the problem where we have actually specific data and points, so on and so forth, that's a point estimate. Okay, the point estimator is sort of the idea of a statistic being estimating the population parameter. Okay, so that's the point estimator. And to do this, we need to find, in order to find the margin of error, we need the standard deviation of the sampling distribution of the point estimator. Okay, and so we're interested in the sampling distribution. It's going to help us determine all the formulas that we're going to use. And so the sampling distribution for P, if you remember way back in Chapter 7, is this, that P hat is approximately normal with a mean of P and a standard deviation of the square root of P times 1 minus P divided by N. And this is only true if both N times P, where N is the sample size and P is the population proportion, are greater than or equal to 15, and also N times 1 minus P is greater than 15. Okay, so those are the two things that we need to keep in mind here when we move forward. Okay, always remember that those come along with any time that we talk about a sampling distribution for P hat, those two conditions will come along. Okay, so now we need to, the point estimator, or the point estimate, is pretty simple. It's going to be the value of P hat. But the real challenge is calculating the margin of error. Okay, so the margin of error is actually made up of two parts. The standard error, okay, so the margin of error is made up of two parts. The standard error, and standard error is very close to standard deviation. Generally in this class, we'll know it as the standard deviation of that point estimator. Okay, so that's why we needed the sampling distribution. So the standard error is the standard deviation of the point estimator, and also some sort of confidence factor. Okay, this confidence factor is very important because it takes into account the confidence level for your confidence interval and the distribution of the point estimator. Okay, so it takes into account both things, both of which are very important to the problem. So it's got to take into account that P hat is approximately normal and whatever confidence level that we choose. Okay, so 90%, 95%, 60%, so on and so forth, whatever percent confidence level that we have, that's going to change our interval. Okay, so the new formulation of our confidence interval is this. Okay, all that I did was split up the margin of error into the confidence factor and the standard error. Okay, so for this case, we know that P hat is approximately normal, so we can use the empirical rule type stuff to inform us about the confidence factor. Okay, specifically, how far should we stretch our interval out so that we can include what we want to include in the interval. Okay? So the real question is, I start at my point estimate, my best guess for the truth, whatever that truth is, and then I stretch it both ways to include my uncertainty about how the point estimate behaves. Okay, so here's some confidence factor terminology. So now we have the standard error that's easy to find once we know the sampling distribution, and we have the point estimator, and then hence estimate, because we know which kind of point estimator we want to use. Okay, so the last thing that we need to do is calculate this confidence factor type thing. Okay, so the terminology that I'm going to use, at least for a confidence interval for P, is that my confidence factor, the actual number that I'm going to use, I give it a symbol, and that's Z with a subscript of alpha over 2. Okay, Z with a subscript of alpha over 2. So you may be very confused, and that's okay, because we haven't really defined any of that. We know that Z is special in statistics and stands for a Z-score. And in fact, we're going to be using a Z-score-ish thing here. Okay. What is the alpha, though? So the alpha is actually 1 minus the confidence level. So if I have a 95% confidence level, then that alpha level is 0.05. Okay, so 95% confidence interval, then 1 minus that confidence level as a decimal, not a percentage. 1 minus that percentage is going to be our alpha. Okay, so it's how much sort of lies outside of our confidence. And so with all of this together, given the fact that p hat is normal, okay, we have this normal curve, and what we're really doing is we're trying to find, we know that p hat is approximately normally distributed, and so we want to find out of these theoretical distribution of p hat, okay, if I want a 95% confidence interval, or just a 1 minus alpha, if I want a 95% confidence interval, that means that 1 minus alpha is going to lie inside where my confidence is. Okay, so 1 minus 0.05, 0.95, that's my confidence level. I want that to lie inside, and then I want to find the points such that that lies on the inside, and then alpha lies on the outside. Okay, so the white space here would be the 95% inside, and then the red and the blue represent the percent of the distribution that lies outside. Okay, so we're going to use our the fact that p hat is normal to get our shape here, and then we're going to use the confidence level, which is 95%, to find where our sort of endpoints are, such that that level of confidence is the area under the curve, or the percent inside in the white, and then the rest would be in the blue and the red. And I know I sort of stumbled around that, but hopefully that made sense. So in our case, z sub alpha over 2 is that point such that alpha over 2% of the distribution lies to the right. Okay, and so that's extremely important. Where that subscript of alpha over 2 means the percent that lies to the right of that point. Percent of the distribution that lies to the right of that point. So 95% confidence interval for P, that means that 0.95 lies on the inside and 0.025 lies on the outside. Now you might say, really, I should say that if 95% lies on the inside of what I want, that means that 5% lies on the outside. But the normal distribution is symmetric. And so if I'm making an interval that has a lower bound and an upper bound, which is usually what we'll do, we need to account for that on sort of both sides. So we split the alpha up into two parts, hence the alpha over 2, to get the points that we want. Okay, so specifically we want to find this value here, which turns out to be 1.96. Okay, that's going to inform us on how far theoretically we should stretch our interval out in order to encapsulate what we want. So before we move on to the final form of this confidence interval, I want to show you how to find that confidence level or that confidence factor. So we'll need to so we're going to use our probability distribution calculator stuff, okay? And we want inverse cumulative probability. Okay? Inverse cumulative probability gives us the point such that alpha percent of the distribution lies to the left of that point. Okay, so I'll say that again. The inverse cumulative probability function here gives us the point at which whatever percent of the distribution lies below that point. We supply the percentage, they supply the number. Okay? We're always going to use, for this confidence level kind of stuff, the mean and the standard deviation of 0 and 1. So we're always going to use the standard normal distribution here. So just leave mean 0, standard deviation 1 alone. Okay? And the value in here is the percent that lies to the left of this point. Okay, so for us, if we go back to our slide here, 95% is in the middle, okay, and I have that 0.025 lies to the right. That means that 0.975 must lie to the left because it all has to add up to 1. Okay, so the 95% plus this 0.025 would give me 0.975. So that's what I'm going to put in here, 0.975. Okay, distribution is normal, mean 0, standard deviation 1. And when I click OK, it should give me 1.95996, which you can round to 1.96. Okay, and you can do similar things with other interval or other confidence levels. Okay, so the common ones that we'll see are a 90%, a 95%, and a 99% confidence interval. We can find others, but those are the most popular ones. Okay, and so we will get those confidence levels for those during our practice. Okay, so let's go back to our slides here. All right, so now that we've found out how to do the confidence level, we're almost there. Okay, we're almost to actually calculating this confidence interval. So the final form, or almost final form, of a confidence interval is the point estimator, a p hat, plus or minus this confidence factor, which I'll call z sub alpha over 2, times the standard error of that point estimator, which we found is the standard deviation of the sampling distribution. And remember, up here, that the sampling distribution for p hat is this. Okay, this is the standard deviation for the sampling distribution of p hat, so we put it there. Okay, so we almost have a formula. But there's one problem. And the problem is I don't know p. Okay, if I knew p, I wouldn't be trying to estimate it. Okay? Remember, I'm calculating a confidence interval for p. So if I knew it, why would I do this? So what we need to do is estimate it with our best guess for p, and it turns out that best guess is, of course, p hat. Okay, so now we have the final form of a confidence interval for p. Okay, p hat is p hat plus or minus z sub alpha over 2 times the square root of p hat times 1 minus p hat divided by n. Okay, so this is the formula that we're going to be working with. So if there's any formula in the past 15 minutes that you needed to write down, it was this one. Okay, so this is the confidence interval for p formula. It'll create two numbers, which are the endpoints of that formula, of the interval. Okay, and of course this is only true, or this is the assumptions that we need to work with when we're creating a confidence interval for p, is that one, the data that we got was obtained by randomization. Okay, so hopefully taking a random sample of some size, but by randomization in some way, and that n times p hat and n times 1 minus p hat are both greater than or equal to 15. Notice again that I had to change p to p hat. Okay, so let's actually calculate a confidence interval. So I give an example here. A recent general social survey, is what the GSS stands for, asked if the wife in a family wants children, but the husband decides that he doesn't want children, is it all right for the husband to refuse to have children? Okay, so the context really doesn't matter. Okay, of the 598 respondents, 366 said yes and 232 said no. I want you to compute a 99% confidence interval for the true proportion of respondents that would say yes. Okay, and so I've already done this work in order not to compromise the quality of this video, and so I'm going to. Okay, and so here I have all the work, and I'll talk through it very slowly so that you can write it all down. So first, in any word problem, which is going to be all of statistics, it's full of word problems, you need to first identify the important terms. Okay, and so if you look at the confidence interval formula for p, you need three things. You need p hat, you need n, and you need that z sub alpha over 2. Okay, so two of them are clear from this setup. Okay, the first and the easiest is that there are 598 respondents, so that's n. Okay, and I'm looking for the proportion of respondents who would say yes, and so that proportion is 366 divided by 598. Okay, which is 0.612. When I say proportion, I mean a percentage. Okay, percentage of the whole, and so p hat is 0.612. Now, from the task that I give you, you also get to know alpha. If I'm computing a 99% confidence interval, that means that alpha is 1 minus 0.99 or 0.01. Okay, and so that leaves me with one last thing to find, and that one last thing is z sub alpha over 2. Okay, that confidence factor. And so I wrote it down here as 2.576, but let me quickly go back to Minitab and show you how I found that. Again, we're doing the inverse cumulative probability. Okay, mean 0, standard deviation 1, and now I need to find the value such that some percent of the data lie below that point. And so you need to do a little bit of arithmetic here. If I want 99% of the data to be in the middle, okay, or included, then that means that 1% is outside of whatever range that I'm including. Yes? Which means if I split that in two, 1% is half a percent, or 0.005. And so what I'm looking for is 0.995. Okay, 0.995, which is 0.99 plus 0.005. So when I click OK, I get 2.5758, which I round to 2.576. Okay, and so that's how I got my z sub alpha over 2. Okay, and now with the n, the p hat, and the z sub alpha over 2, I have all the information that I need. And so I just substitute those values into the formula that we know. Okay, so p hat is 0.612, z sub alpha over 2 is 2.576. Okay, and then the square root of 0.612 times 1 minus 0.612, which is 0.388, all divided by 598, and then you take the square root. So after you do the arithmetic, okay, and come out, the numbers that come out are 0.56 and 0.663. Okay, you get these two numbers with the addition and subtraction up here in the formula, the plus and minus. Okay, so that is the confidence interval for P. The important part here is the interpretation of this interval. Out of everything that you do, I don't care if you can, I do care if you can look through the setup and come up with the numbers that we need, okay, and that you can substitute those numbers into the formula. But what I'm really interested in is if you can interpret what this confidence interval means. And so I know we've briefly talked about the interpretation of a confidence interval, okay, and I'm going to give you a slightly different one here, okay. And so this is sort of what makes statistics confusing, is there are seemingly two different interpretations of the confidence interval, but I promise that they do match up, okay. It just takes a little thought. The interpretation of this confidence interval, and I've actually misinterpreted it, is that I am 99% confident, so that should say 99, that the true proportion of respondents who would respond yes is between 0.56 and 0.663. So it's not really that complicated. You start off really any interpretation in the same way. I am blank percent confident, and the confidence comes from up here. It should say again 99, not 95 in my answer. I'm 99% confident that, and then the next part here comes straight from the problem. Okay, so it says compute a confidence interval for the true proportion of respondents that would say yes. Okay, and so that's exactly what I write here. The true proportion of respondents who would say or respond yes, okay, is between these two numbers. Okay. Again, confidence is not in the actual endpoints here, but it's in the method that I use to create the endpoints, i.e. this formula up here, p hat plus or minus z times the square root of p hat times 1 minus p hat divided by n. Okay, that whole thing. That's the method that I'm confident in. Okay, so now with that information, armed with that information, it's time for, excuse me, sorry, I have one. I want to talk a little bit about the effects of n on a confidence interval. So the effects of a sample size varying and the confidence level varying. So we have to hit a sweet spot in confidence intervals of being precise versus being confident. Okay, in the example that I always give, and it makes more sense in a non-coronavirus semester, is that I could say that I am 10% confident that Shippensburg is going to win between 7 and 8 games this semester in football. Okay, so if we had a football season, I could say that I am 10% confident that Shippensburg is going to win between 7 and 8 games. And the problem with that is that you wouldn't take me very seriously because I'm not very confident. Whereas I could also say I'm 100% confident that Shippensburg is going to win between 0 and 12 games. Okay? I was very confident, and so you should trust me. But the problem is there that I've included every single possibility. In order to be 100% confident, I have to include the entire range of possibilities. So I need to strike a balance between being too confident and creating a really wide interval and being non-confident at all, but creating a really small interval. Okay? So, i.e., as the proportion, as the confidence goes up, the interval gets wider. Okay? So that's one, okay, the effect of the confidence level. But there's also a sample size effect. And so for this, you can look at the formula. As n is going to increase, it's going to make that square root thing very small, or sorry, not very small, but it's going to make it smaller. Thus, as the sample size increases, the interval length decreases. Okay, so these are important things to keep in mind when you actually create a confidence interval in practice. Meaning, you are going to choose that confidence level beforehand, and you're also going to choose how many, the sample size that you're going to take. So if you want to really, if you want to have a confidence interval where you have a lot of confidence in it, but also is not wide at all, you know that you're going to have to increase the sample size by a lot, so on and so forth. So these are important things to keep in mind when you actually create a confidence interval. Now, and there's a summary. Here's the your turn. I gave you a similar setup as to what we had before, and I asked you to compute a 95% confidence interval.